So far we saw Fourier transform, its properties and some examples, and the relationship between Fourier series and Fourier transform. Now we'll see a particular example of solving ordinary differential equations using Fourier transforms. So what are we solving here? We are solving ordinary differential equations of the form like this. So here we have a differential equation in two variables, y of t and x of t. So the degrees of the derivatives of y of t go from 0 to capital N, and the degrees of derivatives of x of t go from 0 to capital M, and they are related given in this fashion. So this is what we refer to as ordinary differential equation in two variables. And if you want to solve this directly, it is quite tedious, but using Fourier transform, this can be solved in a very simple manner. In fact, the way it works is this differential equation gets converted to polynomials through Fourier transform, and it will be easier for us to solve polynomials than to solve differential equations. So before we see how that is done, let's see what this represents. This equation is a representation of what? Basically, it is a representation of a system, and the input of the system is given by x of t. This is the input, and the output of the system is given by y of t. This is the output. So if I have to write output as an expression of the input, then we can say that this is m equals 0 to capital M, Cm times the derivative, Cm times the derivative x of t minus n equals 1 to capital N, Bn the derivative of y of t, the whole scaled by 1 by b naught. In other words, if we want to visualize how such a system would look like, basically there is an input x of t, and that input is taken through multiple derivatives. You take the first order derivative, you take the second order derivative, and so on up until the mth order derivative, and then you scale them with a constant. In this case, the constant is C1, C2, and so on, and then finally add them together. So this gives us this summation. Okay, and now what is that added with? That summation produces the output. Okay, so the output is taken back and some derivative is produced from the output. In a similar fashion, take the first order derivative, take the second order derivative, and so on till the capital Nth order derivative. Now scale them accordingly, b1, b2 up until bn, sum them up and add together. Finally, before you take the output, of course, there is a scaling factor. So there is a scaling factor here of 1 by b naught. So this differential equation represents a system whose block diagram looks like this. So basically what we have here is several derivatives of the input combined with several derivatives of the output. So we'll see later how several RC circuits, several RLC circuits could be actually modeled like this. So this actually can represent a circuit. We'll see how this that later. So given that a system looks like this, not only circuits, in fact, several mechanical systems, electrical systems, electronic systems could be actually represented through this model. So this is a very generic model which gets applied in physics, in electronics, in mechanics, and so on. So given a system of this model, how do we solve the input-output relationship? Meaning, how do we find the impulse response of the system? So if we find the impulse response of the system, then we know everything about the system. First, to say that we need to know the impulse response, we need to be sure that this is an LTI system. So take that as an exercise. and check if this is an LTA system. It will turn out to be an LTA system. Because it's an LTA system, we can characterize the properties of the system, everything completely through just by knowing its impulse response or through its frequency response. So we'll now see how to find out the impulse response or the frequency response given any system like this. So all we have now is the equation which looks like this. Now we have to solve this equation. So it is assumed that we know these coefficients Bn and Cn. So once we know these coefficients Bn and Cn, what do we do? First take the Fourier transform on both sides. So apply Fourier transform here as well as here. So if we apply Fourier transform, what do we get? We use the property of the Fourier transform that if x of t has a Fourier transform x of j omega, then the Fourier transform of d by dt of x of t is given by j omega times x of j omega. Now we can use this property repeatedly, meaning what if we had dn dt x of t. So what is the Fourier transform? This is j omega times n x of j omega. So this can be proved exactly through the same means that we used to prove this. Basically, this is a repeated application of the same property again and again, and this is what you would get. So given that this relationship is true, we are going to apply that here, and if you apply that here for each and every term, what would you get? For each and every term, we would have j of omega raised to the power m times Cm times x of j omega. So this is what we have for each and every term. Now since x of j omega is common, we take that outside, and all we have left out with here is a polynomial. So what is this? This is something like C0 plus C1j omega plus C2j omega squared, so on up until Cmj omega m. So we have a polynomial here. Similarly, on the left hand side, when you apply Fourier transform, so we get y of j omega to be the common term, and you take that outside, and you have left out with again another polynomial in j omega. So what we have here is y of j omega times a polynomial on the left. So the spectrum of the output times a polynomial in j omega is equal to the spectrum of the input times another polynomial in j omega. Now if we know this input-output spectrum relationship, from that we can find out the frequency response. Frequency response is after all the ratio of the output spectrum to the input spectrum. So you compute the frequency response. So this is nothing but the frequency response. And frequency response now simply becomes the ratio of these two polynomials. So you get this ratio of these two polynomials. Now if you can somehow find the inverse Fourier transform of this, then you're done. Then you can find out the impulse response, or you can just look at this frequency response, and from this frequency response you can plot. So given that, now let's say I want to know how the system reacts when I feed in an frequency of let's say 10 pi. Now I can substitute omega is equal to 10 pi into this polynomial because I already know Cm and Bn. I can evaluate this, and I'll know that okay, at that particular value there is some, let's say the amplitude is 1. So I can evaluate this for all values of omega, and I can find out what is the frequency response. So this will completely characterize the system. So one more step forward is to find the impulse response itself. So how do we find the impulse response from this point? So we need to take the inverse Fourier transform. If we take the inverse Fourier transform, you can find the impulse response. So there are two ways to proceed. One is to stop at this point itself, because in many applications frequency response is sufficient enough. So if you're satisfied with knowing the output of the system only in the frequency domain, then you can stop at this point. But let's say you want to know what happens to the output in the time domain, then we need the impulse response so that you can compute the convolution for any given input in the time domain and find out what is the output. So in order to know the system's impulse response, we need to find the inverse Fourier transform of this ratio. So to compute the inverse Fourier transform of this ratio, the first thing that we are going to do is write this in terms of partial fractions. So what are partial fractions? Partial fractions are nothing but equations of the form some 1 plus ax plus some 1 plus a1 plus x plus and so on. So there can be some scaling factor here. So these are what we call as partial fractions. So if we can represent this expression in like a partial fraction, then life becomes slightly easier. Why it becomes easier? We'll see that now. So in order to represent this as a partial fraction, we need to make an assumption, and that assumption is that m is going to be less than n. If you make that assumption, then what we can do is that we can represent this as partial fractions. If the polynomial in the numerator has a degree which is smaller than the denominator polynomial, then this partial fraction decomposition is possible. Otherwise, it is not possible. So for the set of systems where you can have the numerator polynomial to be smaller than the denominator polynomial, we can use this technique and solve this set of differential equations. Let us see what happens if we make this assumption. So if we make this assumption, the first step we are going to do is now find the roots of the denominator polynomial. So if I know the roots of this polynomial, and let us say the roots are minus dn, then we can write this expression as the numerator comes here as such. The denominator, we can express that in terms of its roots. Let's say I know their roots, they are all minus dn, and I have capital N roots. So we have roots from d1 up until capital N. So d1 plus j omega into d2 plus j omega, so on up until dn plus j omega. So if n was 2, then it's a quadratic equation, it will have 2 roots, and you will have d1 plus j omega times d2 plus j omega, right? So this is what we are referring to as factorizing this polynomial. So you write the polynomial in terms of its roots. So here we have minus dn to be the roots of this particular denominator polynomial. So once we have these roots, you factorize them, find the roots of this polynomial, then you can write it in this form. So once you write it in this form, now assuming that m is less than n, you can express this as, instead of all the products, now you can express this as a summation of some constant. This fn here is a constant, okay, and just some dn plus j omega. That's all. So how do you find these coefficients fn? That's the only thing that is remaining. We already found out how to know this dn. So how do we compute this dn? You just find the roots of this polynomial and you compute dn. That is done. So only thing that is remaining is to find out this fn. So finding out this fn is not very difficult. It is also quite easy. We'll see how is that. So what we are saying here is that the numerator polynomial times the denominator polynomial, which is factorized dn plus j omega, is equal to this summation, which is the partial fraction, okay, and that is n equals 1 to capital N dn plus j omega. Now just multiply this entire polynomial on both sides. If you multiply this entire polynomial on both sides, then we get Cm of j omega bar m equals summation n equal to 1 to fn plus dn plus j omega times dn plus j omega. Now let us say I want to find out the fn coefficient for the kth term. So you can write this as Fk divided by dk plus j omega times dn plus j omega plus here n equal to 1, n not equal to k, n the same thing. So, we have just taken out one term and we are writing it outside, that is all, otherwise everything else is the same. So, all we are doing is just writing the same equation by taking one term outside, nothing else. Now, in this term we can simplify a little further because dk plus j omega is already contained in this product. So, we can cancel that out. So, if you cancel that out, you get product n equal to 1, n not equal to k up until capital N dn plus j omega plus this entire summation as such. Let us make a substitution at this point. Substitute j omega to be equal to minus dk. If you make this substitution, what happens to the terms here? So, this product becomes 0. So, that product becomes 0 because there exists a term in this product which is dk plus j omega, and you are substituting j omega is equal to minus dk, which means this term will go to 0. If that term goes to 0, then this term will go to 0, which means this entire summation will go to 0. And all we are left out with is just whatever we have here and this term. So, now Fk could be evaluated as summation Cm j of omega raised to the power m divided by product not equal to k dn plus j omega, the whole thing which is evaluated at j omega equals minus dk. So, if you use this expression, then we can compute these coefficients for every value of n from 1 to capital N. So, all we have done is just taken this equation, multiplied with the polynomial itself on both sides, and we have evaluated the polynomial at a particular root. Okay. What happens when you evaluate the polynomial at a root? It becomes equal to 0, right? That is exactly the property that we are exploiting here. So, you evaluate at a particular root, but then you multiply with that earlier here, so that that gets cancelled out. So, the particular term alone remains. So, if you want to find out a coefficient Fn in this case, then what do? You just use the numerator polynomial divided with the remaining factors of the denominator polynomial and evaluate the entire ratio at a particular frequency value, and that frequency value is equal to the root. If you evaluate this, you find this coefficient. So, this is purely an arithmetic technique. Okay. So, once you figure out all these things, then what are we left out with? So, we are now simply left out with the frequency response to be equal to some partial fraction. Now, this is a very nice simplification because from earlier exercises, we know that the inverse Fourier transform of 1 by a plus j omega is in fact equal to e power minus at u of t. So, if this is true, we can simply use that property here to simplify our analysis. So, in order to take the inverse Fourier transform of this partial fraction, we will exploit this relationship. What is the inverse Fourier transform of this summation? Because this is a summation, we can take inverse Fourier transform for each and every term separately. So, what is the inverse Fourier transform for the first term? The inverse Fourier transform for the first term is f1 e power minus d1t u of t. Okay, and do this for each and every term, you get this summation. So, we did not have to do anything, any complex computation, nothing. The only complex computation involved is finding the roots here. So, once you find the roots of this nth degree polynomial, you can find out the partial fraction coefficients by simply substituting for some j omega, and you are done. You find out these coefficients. Once you know these coefficients, you can directly write the impulse response in this form, but there is an assumption here. You have assumed that the roots are unique. What if the roots are not unique? Let's say now d1 is equal to d2. If d1 is equal to d2, then in the partial fraction computation itself, instead of getting 1 by d1 plus j omega, we would have gotten 1 by d plus j omega the whole square. If the root is repeated, then the partial fraction representation changes. Let's say, for example, a root is repeated twice, then the partial fraction would look like fn by dn plus j omega the whole square. Okay. So, because this factor, how would that factor look like? So, that factor is now basically d1 plus j omega, d2 plus j omega up until some dn plus j omega. A particular root was repeated, then you just have a square here, right? Or if a particular root was repeated 3 times, then you have a cube. So, when you write that as partial fractions, then that power also gets transferred into this fraction. So, if we do not assume unique roots, then you do not have unit power, you will have square or cube and so on. So, then the inverse Fourier transform here will change accordingly. So, this is not true. So, as long as you have made 2 assumptions here, the first assumption is that m is less than n and there are unique roots, all you have to do is find the roots of this denominator and then find these coefficients, partial fraction coefficients, and you are done. Once you find the partial fraction coefficients, you just use those roots and partial fraction coefficients in this expression and you have the impulse response, nothing more. And there is a very nice inference that we can make out of this entire circus. So, we found out the impulse response. Can we tell anything about the system by looking at this impulse response? One thing that we can easily tell from this impulse response is, because of the existence of u of t, this system is always going to be a causal system. Okay, because the impulse response is 0 for all negative values of time. So, the set of differential equations that we have here, a system which is represented by ODE is always a causal system. This LTA system is always causal. Okay, now what if the partial fraction roots repeat? In other words, we'll need to know how to find out the inverse Fourier transform of something of this form. So, if we know this, then we need not even worry about repeating roots. We can find out the impulse response for any system even with repeated roots. So, how to find the impulse response for this one? So, we already know that the inverse Fourier transform of 1 by a plus j omega is equal to, this is, let us say, x of j omega, then this is equal to e power minus at u of t, this is some x of t. This relationship we already know. Now, can we find out what happens to the Fourier transform of this one? We need not actually do this integration, we can exploit the properties. So, there is a new property that we will see now. So, earlier we saw that if there is x of t and you take the derivative in the time domain, then we know that in the frequency domain it is just as good as multiplying with j of omega. What happens if you take the derivative in the frequency domain? So, you have x of j omega. What is this? This is nothing but integral x of t e power minus j omega t dt. Just projecting the phasor onto x and that is all. Okay, fine. Now, if you want to take the derivative, so apply the derivative d by d omega on both sides. The only term that is a function of omega here is this. So, essentially this is just x of t d by d omega. Now, what is this derivative? So, this derivative is nothing but x of t. Derivative here is minus jt e power minus j omega t dt. So this is as good as taking the Fourier transform of this term. So you can say that now we will compute the Fourier transform of z of t, where z of t is equal to minus jt times x of t. So this is the Fourier transform of this term. So if you apply inverse Fourier transform on both sides, now you try and apply inverse Fourier transform on both sides, d by d omega of x of j omega is equal to the inverse Fourier transform of z of j omega, which is equal to z of t. This is equal to minus jt x of t, right. So if we have x of t producing x of j omega, then the derivative of the spectrum would have an inverse Fourier transform, which is given by minus jt x of t in the time domain. So we derive this through this formula itself directly, but we need not even have done that. Directly from duality this follows, because we know that this is true. From duality we directly have that this has to be true for the other way around. Now similarly, what if we integrate in the frequency domain instead of the derivative? So we just, let's say, are given some spectrum, we take its integration. So this is once again similar to something which we did earlier. In other words, what are we doing here is we are convolving in the frequency domain with a frequency domain step function. So if we do this, then we'll use the property. We know that convolution in the Fourier domain is equal to the multiplication in the time domain. So the inverse Fourier transform of this term is in fact nothing but multiplication of x of t with the inverse Fourier transform of u of omega, which is the step function in the frequency domain. Let's call that the u tilde. So the inverse Fourier transform of u of omega is what we are referring to as u tilde. There is a scaling factor of 2 pi. So this follows from the properties that we learned before. So what have we done here is we have represented u tilde of t as nothing but the inverse Fourier transform of the frequency domain step function. To find the inverse Fourier transform of u tilde of t, we will use two properties that we already know. The first property is that the Fourier transform of the time domain step function is given by pi delta of omega plus 1 by j omega. And the duality states that the Fourier transform of x of jt is equal to 2 pi x of minus omega. We will use these two properties to find out the inverse Fourier transform of the frequency domain step function. So the first thing to note here is that we have a minus omega here. So for this reason we will have to find out the Fourier transform of the time reversed version. So what is the time reversal resulting in the Fourier transform? There is a frequency reversal. So we have a minus omega here. So delta anyway is an even function. So this just remains as such. So we need to find out the signal here, which is the spectral domain, that is in omega. We have to convert that into time domain. So what do we need to do? We just rewrite that in the time domain as 1 by jt. Okay. So now we have gotten x of jt. So this is x of jt, and if you try to find out its Fourier transform, we know that that is equal to 2 pi x of minus omega. But here what is x? It is u of minus t. Okay. In other words, that t gets replaced with minus omega, which is minus omega. So you have u of omega. So the inverse Fourier transform of u of omega is given by, just bring 2 pi this side, we have So using the properties of the Fourier transform of the unit step function in time domain and duality, we found out that the inverse Fourier transform of the frequency domain unit step function is this expression. Now we'll substitute that here back. So once you substitute that back, what do we get? So we get this 2 pi gets cancelled. So we have just x of t multiplied with pi delta of t minus jt, which is nothing but pi x of 0 delta of t minus x of t divided by j of t. So that's what we have here. Okay, so we started all this to just get these two properties and use them to compute the inverse Fourier transform of 1 by a plus j omega to the power n. So how do we find out the inverse Fourier transform of this term? We are going to exploit these two properties, or specifically we are going to exploit the derivative property. So we can say that the derivative of 1 by a plus j omega is in fact equal to minus 1 divided by a plus j omega the whole square into j. Okay. So now what is the equivalent inverse Fourier transform? So given that this is true, we are trying to find out the inverse Fourier transform on both sides. So in other words, we are trying to find out the inverse Fourier transform of minus j a plus j omega the whole square, and we already know that this is equal to minus jt times whatever is the time domain representation of 1 by a plus j omega, which is nothing but e power minus at u of t, which means the inverse Fourier transform of 1 by a plus j omega whole square is equal to, multiplying with j on both sides, we just get t times e power minus at u of t, or you can just cancel out this minus j minus j. Now we can do this for any nth order derivative like this. So if you do that for any nth order derivative, the general formula that we get is here. So even if our roots repeat in computation of the partial fractions, we can still find out the inverse Fourier transform using these properties. All you have to do is just remember this, okay, or this. So given any system of differential equations, the first step you have to do is use Fourier transform, write them in terms of polynomials, you get the frequency response. Or if you need the frequency response alone, you can stop there. But if you want the impulse response, then factorize this denominator, then you can write them in terms of the partial fractions. Once you write them in terms of partial fractions, you can use this property of the Fourier transform to find the impulse response from there. Now let's see some examples of ODEs. Where do we encounter ODEs when we solve circuit problems? In fact, we have already encountered this. The first problem that we have been solving for a long time now is this RC circuit problem. So there is an input voltage and we are trying to find out what is the voltage across this capacitor in an RC circuit. And we wrote this input-output relationship like this. So this is the input-output relationship. So if you see this relationship, then you can compute the Fourier transform of both sides. You can see that x of j omega is equal to 1 plus RC j omega times y of j omega. Okay, so this is just plain RC circuit equation which we have derived before. We're just going to use that, and all we are doing is taking the Fourier transform on both sides of this time domain system representation equation. From this we can say that the frequency response is just y of j omega divided by x of j omega, and that is equal to 1 by 1 plus RC times j omega. The nice thing here is, here m is less than n. The numerator degree is smaller than the denominator degree. So after all, this relationship is holding true here, which is good for us. And here life is already simple because you don't have to factorize this denominator polynomial. It is already in the form of the partial fraction. So from this you can directly write that you can just take RC common. If you take RC common, you have 1 by RC times 1 by RC plus j omega. So this is the expression that we wanted. So this is of the form Fn by dn plus j omega. What is Fn here? Fn is 1 by RC. What is dn? dn is also 1 by RC. So from this we can directly say that the impulse response h of t is equal to Fn e power minus dn t u of t, right? What is Fn? 1 by RC. What is dn? 1 by RC. So remember how we derived the solution for this equation in a very tedious manner earlier. Now by studying all these Fourier transforms, life has become very simple for us. So the impulse response now can be derived in a very simple manner. You just write this input-output relationship. Even though there are derivatives, integrals involved in this, we just in 3 lines we are able to find out the impulse response. So this is the power of Fourier transform. So we saw a lot of complicated ways of deriving properties, but once we know those properties, we can apply those properties to make our life simple. So learning that might be complicated, but once you learn it, you can apply that in several circuit analysis to analyze the circuit in a very simple fashion. Now let's see this circuit. So what is this? This is an RLC circuit. So basically we have an input source, there is a resistor, there is an inductor, and there is a capacitor. This is an RLC circuit. You apply a voltage here x of t and you observe the voltage here y of t. Now what about finding this output? Once again, all you have to do is just write the time domain differential equation. This is what it is. So let's say there is a current here which is I of t. Then you can write that using KVL. This is just the KVL equation. Okay, the KVL equation gives you this expression. Now all you have to do is just say that this expression is y of t, that is my voltage across the capacitor. So from this expression you can write down the final input-output relationship and then compute the Fourier transform on both sides. If you compute the Fourier transform on both sides, then you get x of j omega is equal to y of j omega of 1 plus LC j omega whole square plus RC times j omega. So now what is the frequency response? The frequency response of this system is h of j omega equals 1 by 1 plus RC j omega plus LC j omega square. Now you have a quadratic equation. So now you will have to use partial fractions. You will have to compute what is this d1 term and f1 term. f2, you know that there are 2 roots for this equation because this is a quadratic equation. Now you use your quadratic equation solution here, find the 2 roots. Once you find the 2 roots, then you can find out d1 and d2. The next step is to find f1 and f2. Then use the partial fractions technique, find out f1 and f2, and then all you have to do is just write it in terms of the final impulse response, which is the exponential, decaying exponentials. And that gives the impulse response of the RLC circuit.